on this computer so that we have a copy. Yes, so if you have any questions, please feel free to interrupt, and we deal with them as we go along. So that's the basic idea here. The basic idea is you have a square matrix, and you can find some vector such that if you multiply that vector by the matrix, it's the same as stretching the matrix by a factor, lambda. So the lambda is the eigenvalue, and the vector is the eigenvector. So all this can be done by the computer, so you don't have to worry about how these are obtained. The computer will do that for us. We're just illustrating the concept so that they make sense when we get to the coding. So this simply shows how you compute the eigenvalues and eigenvectors. It's a bit technical, so may not be useful to all, but for those who are familiar with this, then this is how you compute the eigenvalues and the eigenvectors. All this will be easily computed in R, so we shall see that when we do the illustration. Unless there are any questions on this, I will just brush over this slide. This was put here for the mathematicians, the ones who really want to see the mathematics. So another concept that is useful is diagonalization, and it's related to the eigenvalues and eigenvectors. So here you need you have a square matrix, and if it has n distinct eigenvectors, it is possible to write it in this form, where P is an invertible matrix, B is a diagonal matrix whose entries in the diagonal are just the eigenvalues of the matrix. So the key thing is that it must have, it's a square matrix, n by n, and it must have n distinct eigenvectors. If it doesn't have n distinct eigenvectors, then this will not be possible. But again, this is very useful. So the matrix P, the columns are simply the eigenvectors of A. So an n by n matrix can have at most n eigenvectors. So, and those are the columns of the matrix P. And I'll repeat again, D is a diagonal matrix with the entries being the eigenvalues. We will see an example of this at some point. Now, one of the uses of this eigenvalue decomposition is if you want to get powers of matrices, it makes it easier, because if you raise A to some integer k, it's the same as just, you don't do anything to the matrix P and its inverse. The only matrix you bother with is the diagonal matrix, which is very easy to find powers of. So this is one use. This appears a lot in these Markov chains, studying population dynamics. I think some differential equations things also use this as well. But this is not our focus. I just thought I should point it out. So there are situations where if you can get an orthogonal matrix that diagonalizes the matrix A, that would be very convenient. And that happens when A is a symmetric matrix. Remember, we mentioned a symmetric matrix before. So when A is a symmetric matrix, the diagonalization is much easier, because the inverse of the matrix P is just its a transpose. So life is so much easier when you have a symmetric matrix, because you can get an orthogonal matrix P, which will diagonalize A. Again, this will become clear. We shall see some examples as we go along. So the other thing that you can look at now is singular value decomposition, because diagonalization does not work for all matrices. It only works for some square matrices, not even all square matrices. So it's useful to find a decomposition that works for any size of matrix. And that's where the singular value decomposition comes in. So for the singular value decomposition, you have a matrix which is of size m by n, we will work with the assumption that m is bigger than n for now. So even the other way around, you would still be able to work it out. So if that happens, it's possible to split this into a product of three matrices. So you have a matrix U on the left-hand side, and a matrix sigma in the middle, and another matrix V transposed on the right-hand side. So these two matrices, U and V, are orthogonal, and sigma has a block of sigma is a diagonal matrix containing, with the diagonal elements being the singular values, what we call the singular values. We shall see how to obtain those in a minute. So this describes the matrix. So this is a decomposition, the singular value decomposition. This is what it will look like. I've given an example because now this is really important for what we're going to do. So we consider a 4x3 matrix. So each column here is a vector containing 4 entries. It's a 4 tuple, U1. They're all vectors. They're just columns. Then this is the matrix sigma in the middle, and these numbers here are called the singular values. So usually these singular values will be non-zero, or at worst case, they'll be 0. And here you have a matrix V, and you get the transpose. So the rows, the columns become the rows. The columns of this matrix V are now turned into the rows. So this is the decomposition, what it look like in general. So to work with a specific example, so this was worked out earlier. Here I have a 4x3 matrix. I've decomposed it into this U, and then there's my sigma. You can see sigma has this block square matrix. It has a block which is a square, and that square matrix contains the singular values. Now we usually will order this in descending order. The singular values are in descending order. So you can see 2 is bigger than square root of 2, and square root of 2 is bigger than 1. Then we have a 0 row here, and on this side we have the matrix V. So since it's a 4x3 matrix, the matrix U will usually be a 4x4 matrix. If you take the full version, you can see we are talking about the full singular value decomposition. The matrix V will be a 3x3 matrix, and then this sigma matrix will be 4x3. Right? So that would work for any other dimensions. Where I put 4, you just replace it with any other dimension. The row dimension for your matrix. Where I put 3, you can replace it with the column dimension for your matrix. So also these matrices U and V are orthogonal, and that makes it useful for us to work. Again, the computer will do this for you. You don't have to do it by hand, but if you run it in the computer, all this will be computed. So how do we, I'll just go back one slide again. Now you notice there's a 0 row in this middle matrix. What that means is that we can knock out one of the columns in the matrix U. We can knock out one of the columns in the matrix U. And we still lose nothing. So we can make this smaller. We can, the pure mathematician maybe is the one who would be happy with keeping all this, but if you're applying this, you need to be worrying about resources. So you can knock out you knock out one of the columns in U, and you knock out one of the rows in sigma, and we still are fine. Now, if any of the singular values were 0, if say the third one was 0, then that means you can still knock out one more column, and then in that case you'd also have to knock out one of the rows in the last matrix here, and you would still get the computation will still give you the full matrix. So this version is what we call the thin or the economy SVD. And you can get rid of the extra 0 rows and also get rid of some columns on the left-hand side and some rows on this right-hand side. Then you have the thin SVD, which takes up less space and is more efficient. So now we have done that for our matrix. Now we have a 3 by 3 matrix here. This is still 3 by 3 because none of the eigenvalues, sorry, none of the singular values were 0. And this is now 4 by, U was 4 by 4 before, now it is 4 by 3. So this gives us a thin version, which is which takes up less space. So now it is possible to expand this matrix in terms of these vectors U, the singular values, and the vectors V in the matrix V. And this is what it would look like. So you basically break this as a sum of rank 1 matrices. And remember, this sigma 1 is supposed to be larger than sigma 2. And the order descends. This should be sigma 3, not just sigma. Slight error. So what this means is that you can get an approximation of this matrix. This was the whole matrix, but you split it into a sum of 3 matrices. So if depending on the values of these singular values, so if sigma 1 is very large and sigma 2 and sigma 3 are very small, if you want to approximate the matrix, you can just drop off the last 2 and you're left with the first 2. Now, the beauty of this is if you want to, for instance, images are stored as matrices. So if you are going to store this in a computer, instead of storing the whole image, you'll just store this vector U1, the vector V1, and this singular value. That will be enough to reconstruct the image instead of storing all the values in the image. So we can see how that works. So here is the whole matrix. We are writing it as a sum of 3 rank 1 matrices. Now, if you want to get the approximation of this, you can ignore the remaining 2 terms in this expansion and just keep this first one. So you can have a rank 1 approximation, and then a rank 2 approximation means you go up to the second term, but you can get a full rank approximation, which not really approximation. The full rank now will give you the exact value of the matrix. So this is how it would look like. So our interest in image compression is the image will be represented as a matrix like this. Now, once it will have way more values than this, so it means the singular values will be also many. And it's possible to see how many will give us an accurate representation of the image, and then we ignore the rest. The rest are kicked off as an error. So for instance, we could pick the first 2 in this case, ignore the last, and maybe the representation will be sufficient for us, will be sufficiently accurate for us. Again, we'll see all this in the R coding as you go along. So this is just what I've mentioned. An image normally will be represented as a matrix. The entries usually will vary between 0 and 255. If it's a color image, it will have 3 layers. We shall be working with the black and white image, which has only 1 layer. These values from 0 to 255 sometimes can be scaled to be between 0 and 1. That is also another way of representing the matrices. Now the values will represent the intensities of the colors. So here is an example. We shall see how this is done in R. So the original image is here at the bottom. It's a bit small, but I hope you can see it. So the original black and white image is at the bottom right-hand corner. This one I'm pointing at. Then the approximations, we start with the rank 10 approximation. You can see the rank 10 approximation is not very clear. It's a bit fuzzy. But as you increase the rank, if you move to rank 20, it gets clearer. And by the time you get to rank 100, the image is almost as good as the original. So the full rank for this image was I think it was 240, but by rank 100, so you have knocked off 140 components, and you still have a fairly accurate representation of the same image. So we'll see how this works in the coding, but this is basically what it means. Now you have, if you are this way, you're able to compress the image. You're able to store only the vectors at a few vectors instead of storing the whole image. And anytime you need the image, you just reconstruct it using the few vectors, and you have less to store on your computer. Although this is not the most efficient way to compress images, but it's a good way to illustrate the power of singular value decomposition. Okay, so I'd like to move to the principal components analysis, which is the star. This is the main application we're going to look at. So unless there are questions on the previous section, are there any? So principal components analysis is a very useful dimensionality reduction technique. So it basically tries to reduce the variables that you have into a smaller set of variables. And the smaller set of variables are supposed to contain as much information as possible about the data. So the content is measured by the amount of variation that is accounted for. And we'll see that in a minute. So it has a lot of applications. You can filter noise from signals, feature extractions in data analysis and data mining and so on. You can interpret the data through visualizing it, so on. And also the interpretation by being able to group variables that are highly correlated into factors, if you like, and so on. The applications are many, but we'll focus on the one. So here is how it works. How do you reduce the dimension? We'll start with a two-dimensional case. So here is your data in 2 dimensions. So you have only 2 measurements, x, the variable x and the variable y. Then you plot them in the... So initially you can see it appears, it makes it look like you actually need x, the 2 dimensions to represent this data. But by rotating this data, it might be possible to find a way to throw away one of the dimensions and still remain with a representation that retains most of the information. So how you do that is the following. First, you find a direction in which the variance is as high as possible. You maximize the variance in that direction. So clearly it's this direction. The variation is much higher than that. So this first direction is what we call it the first principal component analysis. It will have the highest variation. Then you look for another direction which maximizes the variance in the data, and you can see the other direction that varies is now above and below this first principal axis. So this becomes your second principal component, and we want it to be perpendicular to the first principal component. That way, the new set of coordinates that will come up with will not be correlated. So there you are. After the rotation, if you rotate this so that this first principal component is horizontal, you end up with this kind of thing. So now, if you look at this carefully, most of the variation is just in one direction. The second direction does not have as much information. It's very little variation. So we can ignore the second direction and just work with the first direction as follows. So what we do here, we have zoomed in on the y-axis. So the points seem a little further apart than they actually are because you have zoomed in. So what we do is we pick the points and just drop them perpendicularly onto the x-axis. Then you can see these blue circles. That becomes your new, each data point is now represented by just the points along the first principal component. And this is what it would look like. So you end up now with data along just one direction. You lose some information, yes, but maybe not as much information. It may not be significant because there's very little variation along this second principal component. So you just retain one dimension, and that reduces the dimension of your data, but you still have quite a bit of information in the data. So I don't know how helpful that is, but would be the motivation for the principal components analysis. In most of the cases, you will have a larger data set, more than 2 variables. So suppose here you have k variables, this would be your data set. So you set it up as a matrix. The entries are all these in here. This on the left-hand side, these are just the labels. And the variables are these capital X1 all the way up to capital XK. So this is your initial data. Usually the variables may be highly correlated. And also there may be too many for you to make any sense out of them. The aim is to now find a small, new set of variables. So the other thing is, if the variables are many, you may want to reduce or knock off some of them. Initially, there is no reasonable criteria for kicking out any variable. You don't know which one is more important than the other. It would be a bit random to just kick out the variable. So what we do is we transform the data as follows. We come up with a new set of variables, y1 up to yk, which is just a linear combination of the original variables. And we do it in such a way that the first variable has the most variance, or accounts for the most variance in the data, and the next one accounts for the next smallest, and so on. So this is the largest variance, and it keeps reducing as you go along, and yk will account for the smallest variance in the data. But each of them contains information on each of the original variables. So you don't lose the information in the data. So the other thing is that we also set up these variables to be uncorrelated. And this is what you have. This is a transformation. So this is basically what you do. You have a set of data, you transform it into a new set of variables. Each of these new set of variables is a linear combination of the original ones. And then there is some magic that happens in between here. And that is what we shall look at. The computer does the magic for you. Whatever happens in between here, the computer that does that for you. So we shall represent this data set as capital X. And we shall use the letter T to represent this matrix that contains the transformed data. So this is this just repeats what I was saying. This variance is in descending order. So but how do we get this transformation? Remember, we agreed to call our data matrix X, but what we're interested in is getting the new transformed data. Now the new transformed data will have as many variables as the original one, and we have to transform the original data using some matrix V. So this matrix V is simply obtained as it contains the eigenvectors of this product, X transpose multiplied by X, this matrix. Usually the units of measurement for these variables will be different. Some may be way larger than the others. So what happens is for them to be comparable, the data is scaled. It's scaled so that it has 0 mean and variance 1. So before you do the analysis, we shall assume that the data matrix has been scaled to make the variables comparable, so that no one variable is given more importance than is due to it. So this is basically a transformation. You have T, X is transformed using this matrix V. Yeah, and this matrix V is obtained from the singular value decomposition of X. I don't think I included that. I can write this down here. What I mean is this. This matrix X can be split using the singular value decomposition as a U sigma V transpose. So this matrix V that is obtained from this decomposition is the same matrix here that is used to transform. So this V can be, the computer does that for you. You just get it, multiply your data by this matrix V, and you get your transformed data. Of course, we assume that the data has been scaled, so it has zero mean and variance. Each variable has zero mean and variance 1. Okay. I need to get out of this one. It's refusing for some reason. Okay, so that's how you get the transformation, and that's the most important thing. Then once you have a transformation, I'll go back a few slides again. This first, the variables, the variance is decreasing as you go along. Maybe by the time you get to the first two, you will have most of the variation that you need. And you can just work now with the first two variables instead of working with all these K variables. And these first two variables will still contain information. Since a lot of the transformation is orthogonal, these are orthogonal matrix, the distance is preserved. So the distance is preserved as much as possible between the points in the higher dimensional space compared to the lower dimensional space where you only work with 2 coordinates. Now, the beauty of this is that when you work with only 2 variables, you can now plot it and see some patterns in the data. When you have K variables, more than 2 variables, it's very difficult to plot, and you will not be able to visualize your patterns in the data. So the main thing is that now you have these 2 variables, which you can plot, and if there are any patterns that are clear in the data, you should be able to see them at that point. There's more that can be said, but I'm trying to say as little as possible. So this is still talking about precisely what I was saying. You can use fewer variables, and then you're able to visualize the patterns in your data. So the number of new variables that you retain will simply be determined by the amount of variation that they explain. In our case, we'll be targeting the first 2 only because we want to do visualization. You can do a few more if you have other ideas or other things you want to do, like variable selection and so on. But we are interested in data visualization for this case, so we shall just focus on the first 2 principal components or the first 2 new variables that are generated. So our software of choice will be R that we shall work with, and you can obtain it from this comprehensive R archive network. So this is rproject.org, and then you also need the IDE. This is for a graphical user interface that you use. Will be R Studio, but it runs R in the background. So I'm working with R because I've done it in R before. It is just convenient, but you can do this in Python very well. Maybe I will convert the code into Python at some point and share. So I don't know if there are any questions. We proceed. So we look at some practical examples. Here, the first example we look at is a food science example. So the data here contains, I think there are 12 or 13 variables. I forget the number, but you have 4 flour varieties which are made from bananas. Some are made from pulp and some are made from the peel. And then you have those that are made from the ripe pulp, ripe banana pulp, and ripe peel, and also those are made from the green ones. So you end up with 4 varieties in total. The bananas here are called Cavendish. So they take these measurements on each of these flours. They measure the pH, the total soluble solid, the water and oil holding capacity at different temperatures, and some color measurements. I can't say I understand all of this. This is best understood by a food scientist, but we'll try to make sense out of it. And if anyone has expertise in this area, feel free to contribute. So they're given labels. These flours, they are given 4 different labels. So GPE will represent the flour from the green peel. RP is the flour from the ripe peel. And this is the green pulp. And this is the ripe pulp banana. So I hope you will remember that. So that's what the data looks like. For some reason, I can't find the eraser for this. Usually there's a bar that pops up with the, oh yeah, it's just in the wrong, I found it. This particular one is putting it on the side instead of at the top. Good. So this is what the data looks like. It's just a screenshot of the data and some of the variables that we mentioned. So you can see it's all numerical data. And we have 13 numerical variables. If you try to visualize this, it's quite difficult. 13 are too many. So we check the variances for the variables, and you can see some have very large variances. And because of that, it's necessary to scale the data so that the variables are comparable. And the importance of these variables with large variances is not exaggerated. So this is useful to check the variances so that you see if there's a wide variation in the variances of the variables. One way to visualize the data is to do pairwise scatter plots. We've done this only for the first 3 variables, and you can see it's difficult to keep track of this. But even with this basic visualization, you can see some patterns. Yeah, there seem to be some groupings that happen. And this is picked up by some variables, but not some others. You can also check that there are some correlations that are given. This graph gives the correlations as well as some density plots, and so on. So this is a correlation matrix itself, and usually we are interested in PCA works better when you have variables that are highly correlated, and you can note some high correlations here. You could do a hypothesis test to check the significance levels and so on, but in this case, we are not going to do that. But you observe there are some high correlations. That is good for us because it means there are variables that can be grouped together, the ones that are highly correlated. So if you run the summary, the PCA, once you run it on the computer, it gives you and do the summary, you will get the different variables. So this comp.1, comp.2, and so on are the new variables. What is given here are the standard deviations for each variable, which now are the singular values that were appearing in the matrix. And we have 13 of them. Now, how much variation they explain is given in the second row. So you can see the first component explains about 45%, the second one 30% approximately, and so on. But with just the first two, cumulatively, you have 74% of the variation explained. And that may be sufficient for our purposes. So instead of working with 13 variables, now you can work with only 2 and still retain 74% of the variation in the data. So that's how you do the dimensionality reduction. So this is another way to figure out how many variable of the new principal components to retain. And this simply is a graph of the variances of each component. As you go along the x-axis, you are going component by component and plotting the variance. The first one has the highest and so on. Usually you want to cut it off at the point where you have something that looks like an elbow, where there's a sharp change in gradient. Yeah, that is one way of doing it. But like I said, in our case, we're just interested in the first two for purposes of visualization. We shall focus on the first two. So this again, you can do the cumulative proportion of variance. And you can see if you just want to retain about 90% of the variance here, you need a little less than 90% rather. You need the first three. If you want more than 90, you would have to go to the fourth as well. So this is the matrix V. Again, the computer will produce this for you. This is the matrix V that transforms your data, and they are called loadings. The transformed data is usually referred to as scores. So this is the transformed data now. After it has been scaled, it is transformed. And these are your scores. So this is a new data set that you're working with. And if you're going to visualize, you just plot these first two principal components and you'll be able to see some patterns. So we will do that. And you can see when you plot the first two components, you can see some clear separation between the different varieties. So in this case, the separation is perfect. And this is not always the case in real life. Most of the times you won't have this kind of perfect separation. But this is a good example. Also, the sample sizes in each variety are a bit small. So maybe you need a lot more to get a more reliable pattern. So this means you could use this to classify or do some predictions as follows. If you have some measurement from some unknown banana variety, you could project this onto the first two dimensions. And when we do that, it lands on the ripe peel variety. So ripe peel variety is this cluster here. So this is not the other ways of doing prediction. This is not the best way to do prediction, but it also helps. So I created some new data point here. I projected it onto the first two principal components, and it landed this red spot. This is a new data point that we didn't know, we couldn't classify. But after projecting it, it appears to be this ripe peel variety of flower. So this is the essence of it. Once you move from 13 variables, you're able to visualize it in 2 dimensions, and now you can see the patterns. You can clearly see that it's possible to classify the different flowers based on the 2 principal components. Instead of working with 13, now you just work with 2, but you're still able to pick up the patterns in your data. I should have made this graph a little bigger. Maybe I didn't edit it. But I hope it's serving the purpose for now. They should be clearer as we go through them. So this is just the biplot. It also tries to the arrows that are close together shows the variables that are more correlated. So if you look carefully, you can see along the first principal component, it seems to have show a contrast between these color variables and these variables for the oil holding capacity and the water holding capacity. Again, I should have made this bigger. It's too small. Then the second principal component seems to draw a contrast between the water holding capacity and the oil holding capacity, because you can see the oil holding capacity is on the upper side, the water holding capacity is on the negative side of the second principal component. So that's one way you can interpret it. This allows you to do some grouping of the variables, which we are not working on for this talk. So that's the first milestone we have achieved. So some celebration for the first milestone. There are a few other applications. One of them was from political science. So this one is from this Latin American public opinion project. In the code, I will give you the link to the document which has more information on this. So they measured some variables, about 11 numerical variables. There were more, but 11 were picked for this analysis. And when you apply principal components analysis, you're able to get these two dimensions. And it seems to suggest that there are three different political groupings in terms of opinion and so on. Different variables were set up. You will see all this as we go along. So initially you had the 11 variables. With the 11, it's very difficult to extract any patterns, but if you reduce them to these two, you're able to find these political groupings. Once you find the grouping, you can go further and now analyze, see what variables, what are the descriptive statistics for each of the groups for the given variables. That might be able to help a social scientist or political scientist come to some conclusions. So, but again, here the aim was just to find the patterns, and we can see there's a pattern of three groupings politically. Then there's one more from the health sciences. This is from the famous Wisconsin breast cancer dataset. There are about 30 numerical variables. And after reducing it to 2 dimensions, you're able to observe these 2 clusters, which seems to separate the benign tumors and the malignant ones. So then with this, it's possible to use it to assist in diagnosis. So if you have some measurements and you project them onto this section that represent the benign tumors, then it's likely to be a benign tumor. And the same for the malignant tumor. If it projects onto this other side, then it's likely to be a malignant tumor. There are more sophisticated ways to do prediction. And this can be just a preliminary stage to tell you how many clusters you have in your data, or if there are any clusters. And then from there you can use some of the more advanced classification techniques to do classification. But at least now you can clearly see that they're based on the measurements you have, it's possible to separate the benign tumors and the malignant tumors. And this can be useful for diagnosis. So, so now it's time to go to the next level. We need to take this to the next level and do the live demonstration of the concepts we have gone through. Are there any questions before we do that? So I've given a very casual description of the concepts. I hope they made sense. There's a lot more mathematics behind it.
Yeah, hello, Prof.
Yes.
You can hear me? Okay, I would like to add a comment on the...
Just hold on.
On the PCA.
For some reason, maybe my volume is low. Let me see if I can raise it up. Okay. So
it's just
please
a
proceed.
comment on a comment on the PCA.
Pardon?
You know, PCA
Yes.
on the PCA component analysis. So
Yes.
I wanted to comment and say, you know, it depends on correlation. And sometimes, like in real world applications, they usually say correlation is not causation. So if they're data analysts here, they should be careful when they're applying PCA. They should know the data first.
Yes, there are a lot of aspects that go into data analysis. We may not be able to cover all of them here, but you're right. You have to know your data. Sometimes you have to work with people who have knowledge in the domain that you're working with, so that they can share their experience and observations and try to make better sense out of the data. The numbers don't tell the correct story all the time.
Yeah, you can get 90% accuracy, but it can be a different thing. Yeah,
that is
and
true.
Then another comment is on the outlier. Sometimes the PCA performs poorly when there are so many outliers.
Yes, PCA performs poorly when if you have outliers, it's sensitive to outliers. There is another version of PCA called robust principal components analysis, which is a little more recent. It's able to handle situations where you have outliers. The decomposition it uses is not exactly SVD. It splits the data matrix into two components, one with a low rank matrix, and the other one just has the noise. So it separates it has a slightly more advanced mathematics involved, but it can handle the outliers better. So there is a method called robust principal components analysis, which is able to handle the outliers better. This basic one will be sensitive to outliers, but not only will it be sensitive to outliers, it can also help you find outliers. Because, for instance, if you see there are these kind of observations you have, you can go back to the data and see why this one is so different from the others. So it can also help you find outliers. Yeah. So also, if the variables have equal variances, then principal components will not be very useful. If the new variables that you come up with have equal variances, in other words, the singular values are roughly the same, not so different, then again, PCA will not be useful. So yes, it's not it doesn't solve all our problems, but does a good job in quite a number of them. That was a good question. Any more comments or questions before we move to the R?
I have a question.
Yes.
Does it, so that I am clear, does it mean PCA doesn't take care of multicollinearity?
What happens when you do PCA, the initial set of variables can be a number of them can be highly correlated. So that is not good for you. But if you do the transformation, the new set of variables for the principal components will not be correlated at all. That's how they are set up to be. The optimization is done so that the new set of variables have zero correlation, and they are basically uncorrelated, and they decrease in importance. In other words, the variances keep decreasing. So that's how the optimization is set up. So your new set of variables, you will lose interpretation because they may not have, it may not be possible to interpret the variables as anything meaningful, but they will contain information on each of the variables in the original data set. And then they will be uncorrelated. You may now use the uncorrelated data to do regression. If you want, you can use it for variable selection if you wish, and so on. You do the variable selection sometimes by picking. There are other better methods for variable selection, I guess. But you can use it for variable selection by picking the variables that are highly correlated to the principal components. The principal components that have higher variance, or that account for more variance in the data. So I don't know if that answers your question.
Yeah, that's fine. Thank you.
Okay, so let me see if I can share the. Can you see my screen now? I'm trying to go to the. To R. I'll try to increase the size of the. So I've now moved to R. I'll try to illustrate some, at least most of the concepts in the talk. Hopefully this makes sense. Now, the thing is, this will assume that you have some knowledge of R. This may not be the case for some people, but let's just go through this. I will share this code. You can always download R and try to run it as well. I'll share the code as well as the data files that, any data files that we use. So the first here is just setting up a symmetric matrix. This is the code that will create a symmetric matrix, and that's the symmetric matrix. This one does the eigen decomposition of the matrix that we had up there. So this is a this command eigen will extract the eigenvalues as well as the eigenvectors for the matrix A. So if you run it, it will give you those. So the eigenvalues here are 3 and -1, and the corresponding eigenvectors are these ones, 0.7 and 0.7, and the second one is -0.7 and 0.7. So this gives you the matrix P. And we can check that we can reconstruct the original matrix as a product of P multiplied by the diagonal matrix, which contains the eigenvalues, and multiply by the inverse. And when you do that, you recover the, I will just run this. It's a bit slow. When you do that, you recover the original matrix, you can see. So this decomposition works. Now for the 4x4 matrix we had in the talk, you can construct it using this code in R. So this gives you the 4x4 matrix. We can do the singular value decomposition. Again, you just run one command, like I told you. So this gives you the full singular value decomposition. Remember, we have four rows and 4 columns. So that's why you specify these parameters. You do this if you want to get the full SVD. If you don't specify this, it will give you the economy or the thin SVD. But since we want to see both, we'll start off with the full SVD. And it will extract the matrix U, which gives you the left singular vectors, and the matrix V, which gives you the right singular vectors, and you'll also have the sigma. Sigma is the matrix where it contains a block diagonal that has the singular values. I've had to add, because the singular values are only 3, I've had to add a 0 row at the bottom. So it's not correct to make it complete. So if you, this one simply displays the matrices that we have constructed, the U, V, and sigma. So the singular values are here. This is the matrix U, and this is the matrix V. And if you multiply them in the correct order, U sigma, and V transpose, you recover the original matrix. So since there's some redundancy in that full SVD, we can compute the economy SVD. For this, you don't put any parameters here. You just apply this function SVD to the matrix. It will give you the economy SVD. So again, we get the matrices. Now you can see we have only 3 columns for you. Since none of the singular values were 0, we still have a 3 by 3 matrix for V. And again, if you multiply them in the right order, you still recover the original matrix here. So now we can apply this to matrix multiplication as follows. If you pull out the columns U1, U2, and U3 for the vector U, for the matrix from the matrix U, and also the columns V1, V2, and V3 for the matrix V, as well as the singular values, now you can get a rank 1 approximation if you only use the first singular value and then multiply the first column of U and the transpose of the first column of the matrix V. So this will give you the rank 1 approximation of the matrix A. I will run that. Then we display them here. We'll display the rank 1, rank 2, and then rank 3 is just the full matrix itself again. So the first approximation, was it this one? I think this is the first approximation. This is the original matrix A. This is the first approximation using the rank 1 approximation. Or is it correct? Let me check that. So we have the rank 1 here because it uses only the first 2. Okay, A then followed by, yeah. So this is the rank 1 approximation, and this is the rank 2 approximation, I think. And this is a rank 3 approximation. Rank 3 approximation gives you the original matrix. Why does rank 2 look like rank 3? I need to check that, but you can see the rank 1 approximation is just an approximation of original matrix. Instead of 1 in the first slot, you have 1.33. So there's an error. Instead of -1, you have -0.67. So that's an error. But this approximation may not be as bad for us. It may serve our purposes, and therefore sometimes it may be sufficient. This is a small matrix, so it doesn't clearly capture the dimensionality reduction, but it serves as an example. So we apply this to image compression as follows. Because an image is just a matrix, I will just load this library first. So this library EB image is the one that will be used in this section. The original image is colored, so I will display the original image. The original image is a bit big, so it's a bit slow in displaying. So we have a swan, some water, a lake, some boats in the lake as well. Need to move this. Yeah. So that's the original image, and you can see it has 2560 by 1920 pixels. That's the size of the matrix. 2560 rows by 1920 columns. So we will not work with this original matrix. We shall convert it to grayscale. The original colored matrix normally has 3 channels, and you can still work with the 3 channels, but to make things easier, we just work on the on one channel by converting it to grayscale. So this second set of code simply converts it to grayscale, and not only does it convert it, it resizes it to a smaller matrix so that it does not delay the computations. So we'll have a 320 by 240 matrix. That's the image. So now this gives us it's a smaller image now, but it's black and white. The same image. So we just run this SVD on the image because the image is just a matrix inside the computer. When we run this SVD, we're able to extract the matrix U, V, and the singular values, sigma. So using the expansion of a singular value, we can we first pull out an image of rank K, right? So we just use the first K singular vectors, singular values to approximate the image. So I'd set K at 10, and that's what I use as in the calculations. Now, the largest value of K you can get should be 240, right? So, but here we are just picking 10. This will help us see how the compression works. With just 10 singular values instead of 240, what happens? So you can see you get an approximation of the image. The approximation is here. It's not very clear, but you can see it has still captured some structure. We'll get higher rank approximations as we go along. So the next set will generate several different sets. It has rank 10, 20, 70, 50, 70, and 100. The maximum, remember, is 240. So we can eventually we shall compare these compressions with the original image and see how well we are doing. So this code generates all of them. So this one will display some of them. Not the most efficient way to display it, but let's start with that. Then we shall use a loop to display them in a better way. So here are so we have the rank 10 approximation, which is a bit blurry. I think there's rank 20, and we stopped at rank 50. The higher ranks we shall see in the next set of code. But here, what I wanted to also display is at rank 50, you can, whatever is left out, you can see this is what is left out at rank 50. This is the error, if you like, you can call it the error. And you can see what is left out is mostly noise. There's not a lot of structure in what is left out. Out of the 240, you just pick the first 50, and you only left, whatever is left does not have a lot of structure. So most of the structure has been picked up by the first 50 singular values. So now the next, so you can compare, you can use a histogram to compare the compressed image and what was left. So if you look at the compressed, this histogram gives you the histogram of intensities for the compressed image. And you can see there's more of a larger intensities around the center here. But if you look at the error, it has very low intensities. Minus 0.2 is on this side and 0.2 as the largest. It doesn't have the higher intensities. They're all crowded around 0. So what you have left out is mostly noise. So here we can display the approximations of different ranks. That code will do that for you. And then it puts them in one diagram. So you can see the image gets better as you increase the rank. At rank 10, we had seen that already. Rank 20, it gets better. Rank 50 keeps improving. At rank 70, it's almost as good as the original. So that is 70 out of 240 possible singular values to use. And you can compare rank 70 and the original. They look almost the same. Then rank 100 is much better. Almost as good as the original. But you have just used only the first 100 instead of all the 240 possible singular values. Are there any questions on that? Maybe later. So the next example is a food science example we saw. We'll load the data and take a glimpse of the data. So this is the data itself with the variables. If you want to see all of them, they're here. So there we saw the variances. You just used a bar plot. And you can see the variances for each of the variables. Some have very large variances. Others have really small variances. So to make them comparable, you should scale the data. Another way to explore your data initially is to look at pairwise scatter plots. You need a minute or so to run. It's still running. So here you have the scatter plots. There are different versions of them. This is one from the base R, I think. Then there's one from the psych path. I don't know if I included that. You can also explore some of the variables individually. Like this is I think this is a total soluble solid. You can see it seems to have a gap between 2 and 3 scores and so on. This is just data exploration at the beginning to see what the variables tell you. Then you have the scatter plots to see if there are any patterns you can pick up. Now, this is only for the 3 variables. They are a total of 13. So you can see what happens if you have like 100 variables. This it will be very difficult to keep track of these pairwise plots. And principal components analysis will solve that problem for us. You can check the correlations. And when you run that, we had seen this earlier. You have some high correlations as high as 0.9, and so on. There are other ways to visualize the correlations in R. This one does a plot. I will skip that. I think you can run it when you get the code. So we run on the data set, we shall run PCA on just the numerical variables. So we pick from 2 to 14 because the first variable is a grouping variable. Maybe I should go back and just get that. So this is a grouping variable. It shows you whether you have the green peel, the right peel, the green pulp on the right pulp. It's just a grouping variable. So we leave it out of the analysis. So also we have not done any data cleaning because this data was generally clean or had been pre-cleaned. So, and also we don't have a lot of time to go through all the steps. So I'll run the PCA. So the first thing it gives you are the singular values, or if you like, the standard deviations for each of the principal components. And the proportion of variation that is accounted for by each principal component, and then followed by the cumulative proportion. And you can see here by the second component, we already have the 2. But we have 74% of the variation accounted for already. So you can use a script plot to determine how many pieces to retain. Here you get an elbow at 3. If you want, you can retain the 3. But for our visualization purposes, we just need the first two. So this one just shows we pull out the variances. Now the singular values are just a standard deviation. So you have to square them to get the variances. So I've done that manually here, so that we get the variances and plot the cumulative proportion of variances. And you can see if you want to account for more than 90%, you need at least 4 PCs. Now you can remember the matrix V that contains the loadings. We can pull it out of the output. So this attribute, the loadings attribute, will contain that matrix V that transforms the data. So this is a matrix V that transforms the data. You can see the first principal component doesn't seem to contrast any of the variables, but the second one loads a bit high on the viscosity and the total soluble solids. And is negative for the water holding capacity. And yeah, so for the oil holding capacity, they seem to be positive. So maybe it gives a contrast between the water holding capacity and the oil holding capacity at different temperatures for the bananas. If you want to extract features, that's how you can do it. But again, we are not trying to extract the features now. We're just trying to visualize the data and see if there are any patterns. So now we can, what is this now? We can plot the loadings. This is in some sense a biplot, but without the arrows. So it gives you groupings. You can see the variables that are grouped together usually are those that are correlated, and so on. And again, as we had observed in the matrix for the loadings, the second piece of component was giving us a contrast between the oil holding capacity and the water holding capacity for the flowers as well. And that is shown here in the graph. So you can now display the transformed data. So this is the transformed data. So the transformed data is exactly the same size as the original data set, but it's transformed. The difference is now you can now order the variables, and the first two here will contain the most amount of variation. I think we had seen it was about 74%, if I'm not wrong. I can double check that later. So these are the two that we are going to plot now. These first two principal components are the ones you plot. We've just shown the first 6 rows. They should be a total of 48, as many as there are in the original data set. So when you plot them, now you'll be able to see. Now this is just plotting the. What is this? This just the first. This is the first principal component. Remember, the matrix T is the one that contains the scores. We've just picked the first column, which contains the first principal component. And then we are getting the bar plot for that and grouping these by the different varieties. So now I forgot to put the legend. So I'm not sure what colors, but each color is a different variety. And you can see these two varieties seem to score negative on for the first principal component, and these other two both score mostly positive. One lower than the other, but mostly positive for the on the first principal component. So basically, it seems to give a contrast between these two. I think these might both be the peel, and these might both be the pulp bananas. So I think it gives that contrast. So if we plot the first two principal components, now we can clearly see the separation. And yes, you can see the peels are both on the positive side, and the pulp are both on the negative side along the first principal component. So it's able to give us a contrast between those two. The second principal component is not quite clear what contrast is giving us, but it seems to give a contrast between the green and the ripe. The first one separates between the peel and the pulp. The second one seems to suggest that the ripe ones seems to be the ones that are slightly higher, then both green ones are lower. That's again if you want to extract features. For now, we're just looking for the patterns. Nothing big. So this does exactly the same thing, just using a different package. It gives us the same plot of the first two principal components. Now here is I generated a new data point here. So this block just generates a new data point. And these are the values for the new data point. So assuming we have this and we don't know which variety this is, we can project it onto the first two principal components. That is what the next code does. It projects it onto the first two principal components. I think the plot for that projection is down here now. Oh, what has happened to the plot? Oh, it's here. So the prediction lands this new, I colored it red so that we can identify it after the projection. And it lands on this ripe peel variety. And we could suspect now that it is of that variety because it clearly lands after the projection. This is where it lands. It's in that cluster. But then again, that's not the best way to do your clustering. This is we're just lucky that these clusters are quite clear, but in some situations this may not be as clear as this. So this is not the best way for doing clustering or predictions. The other techniques which we will not be able to cover today. So this produces a biplot which also tries to show you the clusterings and so on. And the variables that are closer together are the ones that are highly correlated. So that is the code for the banana application, the banana flower application. I don't know if it has made sense or if there are any questions. I would, in the interest of time, I think I'd like to, we could stop there because we were supposed to stop at 11:30. The rest simply does a similar kind of analysis, but on different sets of data. Or I could just run through that quickly, if that is fine. Do we have any feedback on that? We are already at 11:30. Okay, I'll try to run in the next 5 minutes or so, see if we can do the remaining part. Now, this is the data from the Latin American Public Opinion Project. I have put the link here. When you get the data, when you get the code, you should be able to access this file. This file, it's a PDF file. You'll download it. It has information on how the data was collected. So we there are more than 12 questions, but only 12 have been isolated from the data. And there are about 7,000 people who fill the questionnaires, and we have about 10 countries involved. So this will load the file. And also display the first few rows of the file. So this is just Argentina. There are more, 9 other countries as well. There are several variables. Do I remember? So some of them measure trust in institutions. This one measures whether they opposed some vote. I can't remember which vote. This one measures whether they would support peaceful demonstrations and so on. Quite a number of variables. Then there is some who think whether it's okay to just, this one is a 0-1 variable. This one is also a 0-1 variable. Some of these may not make sense in our, like Congress shutdown may not make sense in our political setting, because that doesn't happen in our setting. But for the political scientists, maybe they understand what happens in Latin America and the kind of setup they have there. So these variables are on mostly on the Likert scale, I think varying from 1 to 7. There may be some controversy on whether PCA should be applied on this kind of variables, but somehow it still gives us some patterns even on this variable. So what I will do, there are over 7,000. What I've done here is I've sampled, I think I'd already done the sampling earlier. Did I mention it? Yeah, at this point, I picked a sample of 100 from each country. So we are only, out of the 7,000, we are dealing with just about 1,000. I picked a random sample from each country of 100. The reason for that is it takes long to run the analysis if the file is too big, but if your computer is strong, you can just run the whole data set. And then secondly, if you have too much data, sometimes the patterns may not be clear. The patterns you're trying to look for may not come out clearly. So this one is just some data exploration. It picks one variable, that is the trust elections variable, and shows it across the different countries, how it performs across the different countries. And most of them seem to be somewhere down in the middle, except Uruguay. Uruguay seems to really, what was the variable? Uruguay, they seem to really have a lot of trust in the elections. They scored much higher than the other countries. But that is not our focus here. So this part simply selects the numerical variables that we shall use for the analysis. Those are the numerical variables. The next one scales the variables. So this does the scaling and omits any cases with missing values if they exist. Again, this is a bad way of dealing with missing values, but we are in a hurry. It's not the best way in all cases. There are more sophisticated ways of dealing with missing values. But I think also this data was clean already, didn't have missing values. So we can get some correlations if you wish. In this case, the correlations are not as high. The highest we have is maybe around 0.4, 0.3, but still there's some correlation. We have 0.5 as well, but not very high. So this is just another way to visualize the correlation. So I will skip that. Now I will run the PCA. This is the usual. For this case, the first two cumulatively account for only 43% for the variation in the data. But again, for visualization purposes, this may be more than sufficient for us. If you want to get, say, up to 75%, you have to go all the way to the 6th component. I will skip the loadings. This one shows the loadings. We were able to cut off the small loadings, visualize any patterns, but maybe we can mention, you see the first component seems to focus mostly on the confidence, but this trust institutions, trust courts seems to focus to load heavily on the confidence in institutions variables. This first one seems to load a lot on these people who can justify a coup or Congress shutdown. So I'm not sure what the political scientists would call that. And the third one loads on these vote opposers mostly. It has a large score on this vote opposers variable. So you can extract some, it's possible to extract some features based on that. This library, this package, Factor Extra, allows you to visualize the eigenvalues better. So it produces all the different principal components, the corresponding eigenvalue, the variance accounted for by each component, and the cumulative. So you can also visualize the eigenvalues using this command from that Factor Extra package. This one, it puts everything in the graph for you, the proportion of variation accounted for. So this is like the script plot. You can either choose to plot the actual eigenvalue here or the percent proportion. So the next one does the same thing, but instead of the proportion of variation accounted for, it plots the actual eigenvalue on each of the components. So this one just shows the loadings in different directions. I will run it quickly. So you can see the loadings on the first principal component. This is the 4th dimension, sorry. So we start with the first dimension of the first principal component. As we saw, it seems to focus mostly on this trust or the confidence variables. That's where it scores high. If you go to the 2nd dimension, it seems to pick up a different cluster or pattern. So these are, maybe it's more about political tolerance. And the third one, vote opposers. I need to check the description. I can't remember what this vote opposers was for, but it scores highly on this one variable. This description tries to explain that. So we can run the PCA and plot the first 2 principal components and see if we pick up any patterns. So I have grouped this by country, but you can see there doesn't seem to be any pattern that isolates different countries. But there are 3 clouds here, 3 clouds that you can see. Now, if you use the whole data set, these clouds may not be as clear as they are now. There may be a lot of overlap, and the 3 clouds may not be so clear. So sometimes that's why it's useful to work with a smaller sample first before you work with the whole, or instead of working with the whole data set. So the country doesn't seem to have any pattern. The countries don't give any patterns, but there are some patterns which are along the 2nd principal components. So you can try to do some classification and see if it's possible to I got curious here. This was not part of the talk. This is just some classification using the K-means clustering algorithm. And I'll just run it without explaining what it is. So the k-means found these three clusters. The blue, it groups all this blue in one cluster. The green and this pink, is it pink? Not sure what that color is. They seem to overlap a bit, but they form the two other clusters. So determining how many clusters should be searched for by this unsupervised learning should not be random like this. You can run some commands to check which is the optimal number of clusters. But this one is just guesswork based on the clouds that we saw in the first one. So, but the k-means doesn't even find the clouds; it finds a different set of clusters. I will skip that. Now, based on the clusters, you can try to see what impacts they have on the variables, and then get some summary statistics on some of the variables, but grouped by the clusters. These are the clusters that have been obtained by the k-means. So this was on the trust media. You can see the three clusters are here, 1, 2, and 3. And the third cluster seems to be quite different from the other two clusters. Cluster 1 and cluster 2 are different if you look at this distribution, but the third one is definitely different from. So you can study this more and see if the clusters have any impact on the different variables. So this is more curiosity about the clusters and so on. I will skip that and this is another. Now, this is now some supervised learning. This is called linear discriminant analysis. I will skip this again and move to a final example for the medical diagnosis. So here we had this data from the Wisconsin breast cancer dataset. I've put the link to the data here. When you get the code, you'll be able to access the data. So if I run this, I will skip the details. We can do the usual exploratory work and check the pairwise scatter plots. Still running. So I can see there are a lot of comments. I have not read them. I maybe after I do this in the chat. This is taking long. I need to get a faster computer. Okay. So those are the pairwise scatter plots for the variables. There are about 30 variables in this case, 30 numerical ones. And then we have one for classification, benign and malignant. That's the one I've used for coloring. And you can see there seems to be some clear clusters for the two classes. That's the pairwise scatter plots. So we can scale the data. Scaling simply means we make the variables comparable. We run the PCA. Now for this one, you can see the first three components will account for around 72% of the variation in the data. I will skip this script plot. We'll just work with the table that we saw earlier. We can also extract the loadings. And also plot the first two principal components. And when you do that, you can see there's a clear separation between the benign and malignant tumors. And that means if you get some measurements on a new unidentified or unclassified tumor, you may be able to use this to classify it as either benign or malignant. So the classification may not be conclusive, but it would be a good starting point for further investigations. Okay, this one I will leave out. It's outlier detection on some image, but I will send the whole file. You can still play around with it. Thank you for listening. We have overstayed, so yeah, I'm just looking at the questions. Oh yeah, there's Collins that asked if there are situations where you can take more than one component. Yes, there are. But for visualization, if you take more than one component, it's very difficult you will not be able to visualize properly. Are there any more questions? Or comments? Yes, oh, so you want to get the code and slides. I think when you registered, you put in your email, so we should be able to forward this.
I have a question.
Yes.
There's something that is really, because when I look at this, I did last time with MATLAB with the image processing. The biggest picture in linear algebra is singular value decomposition, is it?
Yes, so the star of this is
singular value decomposition. You can be able to work in any code to solve a problem.
Yeah, well, it solves a lot of problems. Yes.
Okay.
Yeah, maybe not all problems, but yes, it can help. Anywhere you want to do some, where you need to decompose some matrices, it will help.
Yeah.
You will find it in PDEs. There are certain techniques like proper orthogonal decomposition and so on, which will use this SVD.
Okay.
Where you can split a PDE into a bunch of ODEs, and then you apply this proper orthogonal decomposition to solve the problem, but at a lower rank.
Okay. Fine. Thank you.
Thank you, and thank you for attending. It was a very casual. This basically would be, ideally this should be a fairly long course, maybe like a 2 or 3 day course for it to make complete sense. I tried to squeeze what I could in the 1 hour. Hopefully the pictures made sense as well. Oh, someone is asking if you can use secondary data to inform your research. I think you should be able to use it, but you may not be very confident because you're not the one who collected the data. But if you trust the source of the data, and if the source of the data is reliable, then yes, you should be able to use secondary data. So though my interest in data is largely mathematical, so sometimes I'm not so keen on where the data comes from, because my interest is usually mostly from the pure mathematics side. But if you're going to report if if you're going to write a report that is needed, is important, yeah, it is really necessary to be comfortable with your data. If there are no more questions, I think we can.
Maybe I can ask, are you going to share with us the slides and the code so that we can, I'm curious in learning art of late, yeah.
Yes, I will share this. I will also do it in Python. I just happen to have done it in R already, and I found it a bit inconvenient to start afresh doing it in Python. But writing it in Python is not hard at all. It's possible to convert it to Python as well. I will share this definitely. But a number of people have asked if it should, if they can get the same in Python. When I convert it, maybe I can share as well.
Yeah, thank you so much. Kindly share with us, and then learning is a process. We keep learning new things as we go.
Yes, yes. This is a very powerful technique.
Yeah.
But also acts as a preliminary technique for most other. It's very useful even when trying to do other classification techniques, especially for visualizing the data. There are other dimensionality reduction techniques also that maybe in future I will prepare a talk on. So there are some that are topological. There's one called UMAP. There's one for visualization which is very good at separating the clusters as well. That is, it's called the T-distributed stochastic neighborhood embedding, and so on. The names sound big, but the computer does all the work for you. So there's a lot to do in this topic.
Hello, Dr. Katenda.
Yes.
Thank you for the talk. Thank you.
Yes, you have a question?
Not question, congratulations.
Yeah, I hope it was helpful. Thank you.
Yeah, it is helpful. I'm working on some PCA analysis work.
Yeah.
Once I'm done, I'll share with you to review.
I'll be happy to look at it. And if you want to do some more of the pure mathematics, you are welcome to visit in Chiromo.
No, this is not pure. This is statistic.
Yeah, no.
What I'm working on is just the statistic side. Yeah.
Yes, but it may be helpful to just know what is going on in the background.
Yeah.
We might convert you to a pure mathematician.
Thank you.
Yeah, okay. Thank you. So I think we'll stop there. Thank you all for showing up for this talk.